A very good morning to everybody. I welcome you all for this session 25. In this session, we will learn about generalized coordinates. So let's recap what we have studied in previous class. We learned about virtual displacement, virtual work, and principle of virtual work. An imaginary, arbitrary, instantaneous change in the position vectors of the particle of a system is known as virtual displacement. The work done by the virtual displacement is known as virtual work. A system of particles is in equilibrium only if the total virtual work of the actual forces is zero. This is the principle of virtual work. So the learning objective of this session is to understand generalized coordinates. So by the end of this session, you will come to know what do you mean by generalized coordinates. We all know different set of coordinate system, namely Cartesian coordinates, which are x, y, z. Polar coordinates r, theta. Spherical coordinates are theta and phi. And cylindrical coordinates are theta and z. These coordinates are used to describe the motion of a particle. Let us consider an example of a simple pendulum. Simple pendulum motion can be described by any of the four available coordinate system, like Cartesian coordinates and plane polar coordinates. However, the best choice is to choose plane polar coordinates to describe simple pendulum motion. If x is equal to L cos theta, which is a function of L theta, and y is equal to L sin theta, which is F2, which is a function of L theta, the relationship between them, between Cartesian coordinates and plane polar coordinates, theta is equal to tan inverse of y by x. In a plane polar coordinate system, L, theta be sufficient to describe the motion of a simple pendulum. However, if the length of the pendulum is fixed, then theta coordinate is sufficient to describe the motion of a simple pendulum. Hence, x will be a function of just only theta. Likewise, y will be a function of only theta. Hence, theta can be represented by generalized coordinate represented by q1. So theta is sufficient to describe motion of a simple pendulum. Now let us consider one more example, a particle moving on a surface of an inverted cone. The coordinate system chosen is spherical coordinates, which is given by x is equal to r sine theta cos phi, which is a function of f1 r theta phi. Likewise, y is equal to r sine theta sine phi, which is represented by f2 r theta and phi. Similarly, z is equal to r cos theta, which is f3, a function of r theta and phi. Since the particle moves on the surface of a cone, the angle theta is fixed. Hence, r and phi will be sufficient to describe the motion of a particle moving on a surface of an inverted cone. Then x, y and z will reduce us to two coordinates, namely r and phi. So now r can be represented by q1 and phi can be represented by q2. These q1 and q2 are generalized coordinates. In simple pendulum, theta was a generalized. Theta is equal to q1 is a generalized coordinate. Likewise, in this case, q1, q2 are the generalized coordinates. Likewise, the set of independent coordinates sufficient in numbers to describe completely the state of configuration of a dynamical system, which are represented by q1, q2, q3, so on up to q1, is called as generalized coordinates. The generalized coordinates of a Cartesian in terms of generalized coordinates is given by x is equal to x, a function of q1, q2, q3, so on up to qn. Similarly, y is equal to y, a function of q1, q2, q3, so on up to qn. Similarly, z is a function of q1, q2, q3, so on up to q and t. These coordinates, which are represented by q1 and q2, q3, so on up to qn, are known as generalized coordinates. So we learned in this session about generalized coordinates, which is a set of independent coordinates which are sufficient in number to describe completely the state of a configuration of a dynamical system and are represented by q1, q2, q3, so on up to qn. So now let's have a small MCQ session. Question number 1. R is equal to a function of r theta z is which type of a coordinate system it is? It is cylindrical coordinate system. Question number 2. R is a function of r, theta, phi and t, which is a spherical coordinate system. So answer is D. Coordinate system used to describe the motion of a simple pendulum is, generally we use plane polar coordinates. Question number 4. Generalized coordinates used to describe to steady simple pendulum is, which coordinate is sufficient? It is theta. So answer is C. Question number 5. In simple pendulum, which variable is fixed? You know that length is fixed. So answer is option A. Question number 6. For a particle moving on a surface of an inverted cone, which variable is fixed? It is the angle theta. So option is B. Question number 7. Generalized coordinates used to study simple pendulum is, option is B. Generally, it is both A and C. When it is, if the length of a pendulum is not fixed, So both r and theta are used to study simple pendulum. Generalized coordinates are, you have seen q1, q2, q3. They are depend on each other. So answer is option A. If a generalized coordinate has the dimension of velocity, generalized velocity will be the dimension of. So the differentiation of a velocity is acceleration. So option is answer C. Question number 10. If a generalized coordinate is angle theta, generalized force has a dimension of. Option is torque. Answer is torque. Option is C. So in this session, we learned about generalized coordinate system. Thank you all. Hope you enjoyed this session.